Okay, so in this video, we're going to look at gravitational field and then what we consider to be gravitational acceleration, which is also that acceleration due to gravity. So, as stated, the magnitude of the gravitational force of an object near the planet, near the surface of a planet. Again, we got to distinguish between surface and at a distance, right? So when we talk about near the surface of a planet, right, we're looking at the weight of the object. And then what we can do is manipulate the formula, this formula and the Newton's law of universal gravitation formula to develop an equation for the acceleration due to gravity on any planet, right? And so this is kind of how space agencies do this at this point in time. And so what we do is set the weight equal to the g m1 m2 over r squared equation. In fact, let's change our 1 and 2 to just be m, and then we'll call the other m mass of a planet, the mass of the planet. So we'll say m and big M sub p. But this mass and that mass are just the mass of the object, or any object. And so we say g, the acceleration due to gravity, is equal to g, big G, times the mass of the planet times the radius of the planet squared. Okay, and this r, if you're looking at the surface, is just simply the radius of the planet. But it could also be something called the orbital radius, which is if you're looking for the g value at a height off of the planet. Okay, so one thing to know that is when you increase the mass of the planet, right, or as you get your mass gets bigger, right, in terms of the planet, the g value will also increase, right? And so that's really the two things that the g value is dependent on are it's directly proportional to the mass of the planet and inversely proportional to the radius of the planet, right? So if I increase the radius of the planet, I actually decrease the value. Okay. So this equation says using the known radius of Earth and that of g equal to 9.80 meters per second squared at the Earth's surface, find the average density of Earth. So these are the type of questions now that can be asked now, right? And so what we need to do is we need to really set up an equation. We know the density is going to be mass over volume, okay? But uh, we need to know what is the volume of Earth, right? Or we need to using the equation, this G equals to G MP over RP squared. What we need to do is really figure out what is the mass of the Earth according to this equation without looking it up, right? And so the radius of Earth is 6.37 times 10 to the sixth, right? And so I can take this equation, do some algebra, and I get G times radius of the planet squared over big G, right? And so it's going to be 9.80 times 6.37 times 10 to the sixth squared over 6.67 times 10 to the negative 11th. And that number is going to be 5.96 times 10 to the 24th kilograms, right? And that's according to this number here, 9.80, okay? Now I know that density is mass over volume. And I can solve this for the density, right? Because Earth is a sphere, right? And so I'm going to say 5.96 times 10 to the 24th over, now the volume of a sphere is 4/3 pi r cubed. So I'm going to do 4/3 pi times 6.37 times 10 to the sixth cubed, right? And I plug all that into a calculator and I get an average density of 5,504 kilograms per cubic meter. Okay, that's a lot of like algebra and substituting. What you could also do is, sorry, I'm weird circle there. Sorry about that. So I could kind of take all this right here. So 4/3 pi r cubed. I could take all this and manipulate it to plug in for not right, to plug in for mass. So I'm going to say the mass of the planet is going to be 4/3 pi radius of the planet cubed times the density, and then I can plug that in, and you see that how the formula would get things to like would the formula would have things cancel out, especially the radius of the planet and all that canceled out. But you end up with the same answer regardless of what you use. All right. So here's an old AP Physics C question talking about you have this spherical non-rotating planet that has a radius of r and a uniform density of rho throughout its volume. Suppose a narrow tunnel were drilled through the planet along one of its diameters, as shown in the figure, in which a small ball of mass m can move freely under the influence of gravity. Let r be the distance of the ball from the center of the planet. Derive an expression for the force on the ball at r is less than capital R. So we're going to be inside the planet, okay? And then we're going to do a graph, okay? And notice that how the graph is set up, it is in relation to R. So this is this is what we're deriving, right? Because we actually know what it's going to look like outside the planet. It's going to look something, right, like this, because that's just our standard F equals G m1 m2 over R squared equation. So let's figure out what is it going to be on the inside of the planet. So we're going to do F equals G, mass of the object, times mass of the planet over R squared. Okay. But we know that we can, again, kind of do this manipulation of the density formula. So you're going to get rho V, and the volume of a sphere is 4/3 pi r cubed. Okay. Uh, and so this R is going to be that R on the inside, right? And so I can plug that in. I'm going to say F equals G m 4/3 pi r cubed times rho divided by r squared. Now these r's are actually capital R's, right? Because we're talking about um, the radius of the planet and everything. Okay, and so what happens is these two r's cancel that r up top, and I get a simplified version of the formula of F equals G mass of the object. We'll say 4/3. Let's write this with our constants first, right? And so our constants are 4/3 and pi. So we're going to say 4/3 pi big G times the mass of the object times the radius of where we are, right? Again, this r for us will be little r, which is inside the planet, okay? And so what happens is this is now going to be linear, right? So on the inside of the planet, it's going to be linear. So that's this video. Oh, sorry, there's a couple more blanks here. Um, so if we're talking about a hollow sphere, right, the gravitational force inside that planet will end up being 0. And so this is the end of this video. We're going to look at Kepler's laws of planetary motion next, and then we're going to keep going from there.